So thank you all for joining us this morning. This is webinar number 5 for the PCA. So we're very excited to have been able to offer this winter webinar series this year. And as I mentioned, each time we do abide by an antitrust statement. So I'll put that on the screen now. And we do have our legal counsel, Tony McLeod, on the call with us today. As with all of our presentations, these are vetted through our attorney to ensure that it meets the criteria for the PCA to be able to share it with you today. So all of the slides have been reviewed by our trustee legal counsel. And so, Tony, I will let you make your reminder statements to everyone. I don't think we'll have any issues except for the question and answer portion. So if you'll make the reminder, please, sir.
I'd be happy to do that, Amanda. I think you just gave the antitrust reminder for me, frankly. I would call everybody's attention to the antitrust policy, which is on the screen right now, particularly the second paragraph. Those are the things which competitors are not supposed to discuss among each other. And the reason we don't discuss things like that among each other is we don't want to even create an appearance of impropriety. I have, as Amanda said, reviewed the slide presentation for today's webinar, and I really don't think there's going to be a way that even a fanciful mind can get off the antitrust rails and commit a violation of the antitrust laws on today's topic. However, I will be listening. Sometimes the issues arise the way questions are formatted or presented. And as Amanda said, I will review all questions to make sure that they're fine. With that, if I do hear something that I don't like the sound of, you'll be hearing from me again. And otherwise, let's all look forward to the presentation. Thank you.
Thank you, Tony. So today we do have BDC with us. BDC is the Biorenewable Deployment Consortium, and Ben Thorpe and Harry Siemens will be speaking to us today. BDC was originally formed in 2006 as a regional organization and then expanded nationally to in 2010. Its current name was adopted in 2015 to better reflect their efforts, and BDC serves a very diverse group of nearly 70 organizations, and they have international membership now, which is always very exciting. They represent manufacturers, suppliers of technology, government agencies, and selected academic institutions. I've included BDC's brochure in the handouts today, and you'll find that BDC's mission is to assist the forest products industry by promoting the deployment of commercially viable advanced biofuels, biochemicals, and byproducts technologies, but do not require long-term subsidy, and by optimizing efficiency in order to get the most value from the tree. So BDC and PCA have had a collaboration for several years now, and we continue to partner with one another and share information amongst our organizations. So we look forward to continuing to have a partnership with BDC in the future. And I would like to introduce Harry Siemens and Ben Thorpe to make a presentation to you today and let you know what technologies are forthcoming. So Ben and Harry, I'll turn all the presentation controls to you.
Thank you, Amanda, and glad to be here. Now, I've got to make a confession up front. When I was a kid, and we would drive through Pine Bluff, Arkansas, and the International Paper Mill was there, and I smelled the mill. I swore I would never work in a paper mill, and I kept that throughout the remainder of my next few years. As I continued thinking about my career, went to the University of Louisiana Tech in Ruston, Louisiana. chemical engineering. I kept bugging the co-op director that I wanted to get into the program. That's where you work part of the time as you go in school, and then you go to school part of the time. So he finally called me one day and said, "I've got an interview for you at Continental Can Company down in Hodge, Louisiana. And do you want to go interview?" And I said, "Sure." So I got ready that day, drove down, and as I was getting closer and pulled into the parking lot, I realized it was a paper mill. So I went ahead, I interviewed, I got the job, and I started learning to love the industry. I ended up going to the Institute of Paper Chemistry in Appleton, Wisconsin, and got my master's in paper science. I think the biggest thing I learned at the Institute was that you can tell the difference between 25 below zero and 35 below zero. And that was a real learning for me. I was happy to go back down south after I got my master's. Helped start up the Potlatch paper mill near McGee, which is my hometown, and worked my way up to mill manager, and then later to the vice president of the Pulp and Paper Board division, and lived out in Idaho for a little bit. Retired and came back home so I could be near my kids and grandkids. So I got a call from Ben Thorpe to help them as they were trying to take BDC to a national level, and it's been a great way to help pay back to the industry that I really enjoyed being in. You can see on this slide we've got a great list of advisors, well represented by the forest products industry. The BDC, by the way, stands for Biorenewable Deployment Consortium. It started off as the Biorefinery Deployment Consortium. After a while, we decided it should be the Bioenergy Deployment Consortium, and then as the years went by, we realized it should be Biorenewable. So we were able to keep our initials, but we changed our name a few times. BDC has membership of over 40 companies, and we represent the forest products industry. Members represent over 80% of the pulp production in the U.S. So we're well represented and have a good panel of advisors. Got three logical statements here. Good markets for trees mean healthy and growing forest. It's you have to ask yourself sometimes, are we the good guys or the bad guys regarding cutting trees down? I think the majority or all of the people on this call will probably say we're the good guys, but I've got some data to back that up here in a little bit. We'll get into that, but we certainly believe that. We think that forests are the answer and trees are the answer, and we need to take advantage of them. Economic renewable processes provide viability. We've got a good process now. The processes we use to make pulp and paper are very efficient. However, it always helps to get more value, and our efforts are trying to get the most value we can from a tree. So that's why we look at all of these processes. We're looking at them from the standpoint of how can you get more value? How can we make the industry more viable? And then finally, brokering partnerships have achieved successful deployment. That stands to reason, but we spend a lot of our time and effort working on finding the right partners to go along with the processes that we have done our due diligence on to help make those become a reality, get them proven out in the industry. An example of that I'm going to use is via separations, a new process that concentrates weak black liquor through the use of membranes, and it's a membrane that's been established to that they can withstand the harsh conditions of high pH and high temperature. We help them by helping them understand the industry. We helped them by helping them locate some companies that would be willing to let them put their pilot in their mills so that they could get data from the real environment from within a pulp mill, and they've done that. And Ben will talk more about that later, but they've been successful in 3 trials in this past year at 3 different mills. So let's go to the next. So back to the forest. We want to, we've got a renewable raw material, and most industries can't really say that. We've got one of the most renewable and efficient processes and manufacturing processes in the world, and for some reason we don't get that public relations view of it, and that's a shame because it's the truth. We've got to help get that message across, and it's important to know that things like healthy markets make healthy forest. I don't know if you've heard that or not, but it's the truth. And when there's a value for a tree, then there are trees made available because the motivation incentive is there to do that. We've been able to get some find information. We've put it in some articles that we've written, and I'm going to show you a little bit more about that. So let me just ask you this, think about it a minute. Where in the world do you think is the most net growth of forest? There's they're called net growth, net drain. In most of the world, there's a net drain on forest, and in a couple of places in the world, there's a net growth. So where would you think those would be? They're North America and North Europe, and we found a book. We talked to some people from the Forest Products Laboratories. They had provided information and contributed to a book that I'll show you in just a minute, and you can go find it yourself. But they did research throughout the world and about where there was net growth and where there was a net drain on forest. And as in doing this, this is what they found: is in North America and North Europe, there is a net growth. And then they came up with the reasons for that. They said that, in other words, anytime there's a value placed on wood and biomass by the industry, then there's incentive for people to grow trees. And since 1953 in the United States, there's been they have doubled, the United States has doubled the volume of trees, and actually more than doubled, well more than doubled the volume of trees in the United States since 1953. Everywhere else in the world, there's a drain. And when there's no incentive, when you've got timberland and you cut it down to sell, and there's no incentive to replant it, then you find a way to do something else with that land. It's just logical, and it's just human nature. Now governments can try to force the issue, but the way to really get people behind growing forest is to have value for that tree. And so our forest industry already does that, but by finding these new biorenewable processes to complement what's already being done, then we're just adding more value to that tree. And in that way, we're ensuring that there'll be forest in the future. So BDC, mentioned this before, but we're focused on processes that are valuable to the industry. We're working with the renewable process companies to attain the demonstration or the commercial reality. Ben will go into that a little more later. And then we're working as the intermediate broker to broker partnerships so that we can find those mills that are the best fit, and then we can help them even more by potentially helping them find funding for those plants. But basically, we'll do anything that we can to help assure that those processes that we've done due diligence on and realize they have good potential for the future, that we can get those out there, get them proven, and so to get them accepted by the industry and get them deployed. We're also a resource, and I did all that other first because that's where the majority of our time is spent, in brokering partnerships and finding those processes. But then we also act as a resource for answering questions, for providing information to our membership. We've got a couple examples here of some webinars we've done. Shell Technology aligned with Lucilla. Lucilla is a company that uses supercritical water, high temperature, high pressure water to break down wood. Lucilla is coupled with Canfor in Canada, and they have a JV going to build a plant in Canada, where Shell will also add their equipment to convert the bio crude oil that comes from the Lucilla process into fuels and chemicals. And we've got that webinar that we've done, and by the way, we record those and keep them in our library on the BDC website. I mentioned via separation, they have done a webinar and provided information about the demonstration trials that indicated that they had run. So those are just a couple of examples, but we've got a number of those. Also, we've got face-to-face meetings. We did have face-to-face meetings back before the pandemic. We plan to get those started back up in 2022. But here are a couple of examples of those. Each time we have one of these meetings, or did have and will in the future, we couple it with a tour. And so in the Montreal case in 2019, it was a lignin-based thermoplastics and biocomposites. And we toured the laboratory that was taking these lignin-based plastics and converting them into mainly automobile components. Also in 2018, we were in North Carolina, where we toured TRI, which is a gasification company, and they were coupling Velocity's pilot facility that converts the gases from TRI's process using Fischer-Tropsch into Fischer-Tropsch liquids and fuels. And that process has been announced that it is going to be built in Natchez, Mississippi. So we get to see these things early on, and in fact help with the deployment of these. So we've got a number of these new processes coming online that are going to be commercial, and that's what Ben is going to get into. And I'm going to turn it over to Ben now and let him take it from here.
Thank you, Harry. Is the voice projection good this morning?
Yes, I hear you good.
Thank you. Harry alluded to some commercial processes, and we've been working on a number of processes for a number of years, and looks like in 2022 we're going to have 2 commercializations and perhaps a third. We'll talk more about centrifugal soap separation. PCA is an organization involved in soap and tall oil and other products. And there's a new process. The first unit has been sold and will start up in 2022 in a mill in Arkansas. We talked a little bit about via separations. We need to give a little credit to the Department of Energy, because in 2006, they issued a benchmark study on energy use in the pulp and paper industry. And they got industry averages for what an average pulp mill looks like, an average machine looks like, and what the average energy use was. And they found the highest energy use in the pulp mill was the evaporation of weak black liquor into concentrated black liquor before you fire it in recovery boilers. So that focused a lot of effort on how do we do evaporation better and more efficiently, and that may result in a membrane system which will reduce the energy by perhaps 50%. And whether or not you can take advantage of all that depends on your mill systems, which can be studied one by one. And finally, there's enzymatic fractionation of lignin, which has been demonstrated in the pilot scale. And the pilot is large enough to have made product. And product has been tested in pilot units, the application of lignin, and there are some exciting developments there. The next slide, Harry. Let's skip the next slide and go right on to the technology scan. If you look at the vertical arrow, that scale is low impact to high impact. Where we think these technologies, once deployed and once successful, big question is, what is their impact? And then the horizontal scale starts on the left-hand side in research, proof of product, proof of process, proof of product, deployment, and ultimately commercialization. And this slide shows some short-term developments. And we've already talked about a couple of them. We'll talk about a couple more. We'll start on the right-hand side, upper right-hand with Valmet, and that's lignin separation. The particular process is LignoBoost. There are two large mills that have commercialized this technology, one in Plymouth, North Carolina, and one in Heinola, Finland. This process takes the black liquor from the evaporator train at about 40%, takes a side stream, a slip stream of whatever volume is appropriate, brings it to a small installation where the weak black liquor at about 40% is acidified. So you're adding some chemicals to this process. Once acidified, the lignin precipitates. The lignin then can be separated, washed, and dried. And lignin comes out of the process in rather pure form. And this is done and has been done only in craft mills. So it's craft lignin. And then the effluents are returned to the weak black liquor so that the process in itself doesn't consume anything else except the chemicals that were added, and the chemicals go back to the weak black liquor. That lignin is then available to develop into value-adding products. People who run this process have estimated that in the average craft pulp mill, you can take out perhaps 30% of the lignin and still run the mill efficiently if you can find alternative energy sources. In the United States, an alternative energy source was to co-fire natural gas in a recovery boiler, and this was the view back in 2012, 2015, not the view today. Most companies would not buy more fossil fuel to improve their profitability. There would be a public reaction to that, which would be undesirable. So that puts pressure on energy reduction. There's more than one way to skin a cat, and we look for all ways to do that. But you can take 30% of the lignin out if you can save 30% of the energy. Hence, technologies like via separation become an enabling technology for things like Valmet LignoBoost. And there's a LignoForce that was developed in Canada, running at a mill in Hinton, Alberta as well. Sticking to the right-hand side, the commercialization, Andretz has recently demonstrated converting the mill VOCs to biomethanol. They take the VOCs that would normally go to a combustion unit to be burned, requiring more fossil fuel to burn them. And when burned, they convert to a variety of chemicals which are scrubbed out and taken away from the mill site and put in appropriate locations. This is a costly process, but a necessary process to meet environmental standards in industrialized nations. Valmet has taken this VOC stream, volatile organic material, gaseous stream, and they have learned how to clean it up to get some unwanted compounds out and to convert that stream to methanol. And that plant was commercialized last year at a pulp mill in Sweden. That's a little bit lower impact because it will not be appropriate for all mills. Finally, there's a NORAM technology that has been developed, deployed in, I believe, 6 mills originally, now up to about 10 or 12, where the green liquor and the white liquor are clarified by technologies developed in Sweden and adopted by NORAM, and NORAM developed the equipment to do this. Cleaning the dregs out of the white liquor and the green liquor has immediate energy savings, and ultimately production increases. And again, it's not applicable to all mills, and the production increase possible is in single-digit percentage points versus the Valmet LignoBoost technology, which may have a 30% impact. So that'll give you an idea of how we use that impact scale. The next technology we'd like to talk about is the head engineering and soap separation technology. When mills were originally built, and these would apply to mills pulping pine, and primarily southern pine. The mill was built in, say, 1970. It was a 1,000-ton-a-day mill. The engineers built the soap separation tank of a certain size to take out perhaps 90% of the soap. Well, that mill today could be 2,000 tons a day, but soap separation tank is the same size. So instead of taking out 90% of the soap, it's taking out 45% of the soap. And the soap goes on to the recovery boiler and is burned. It has some energy value, but it also decreases by a small amount the firing efficiency in the recovery boiler, and many believe is the primary contributor to evaporator fouling. The centrifugal technology takes 99% of the soap out. This has been demonstrated in trial units in mills, in more than one mill, and we do get the 99% removal. So it's possible to get a very clean stream of black liquor or soap-free stream of black liquor. The first thing that'll happen is you get more soap and more towel oil to sell. Could double it. Initial installations won't do that, but that's the ultimate impact. And the black liquor is cleaner. We believe, the experts believe, everyone I talk to believes that there'll be less fouling of the evaporators, and less fouling means less loss of energy efficiency between evaporator cleanings. And you'll get a slight increase in firing efficiency in the recovery boiler. When you take the soap out of the black liquor going to the recovery boiler, you also increase recovery boiler capacity. And if a mill can make more pulp, if it has the digester capacity, the washing capacity, and other capacities, more pulp can be made. So this is going to have a high impact in softwood mills and pine craft mills. Whether or not this technology can be extended to hardwood is yet to be demonstrated. Theoretically, it can be. Whether or not it's going to be economical depends on a lot of mill configurations, but this graph assumes it's only for softwood mills. Then the last one on this slide is the via separations. They have had very successful trial in 3 mills on pine, on hardwood, on mixed mills. And in each case, the trial exceeded the expectations that were established for that trial. So this technology runs a little bit better than most folks thought, and will likely be commercialized in next year, 2022. Once commercialized in 1 or 2 mills, this technology will go very rapidly because unlike other technologies like lignoboost, where you have to sell lignin, or the technology of converting VOCs to methanol, where you have to sell methanol, you don't have a product to sell here. You simply save energy. Now, how much energy you save depends on where the steam comes from to go to the evaporator train, and whether or not the mill can save 100% of that steam saved, or some other percentage of that steam saved. So like any of these, you need a lot of analysis to figure out exactly what's going to happen in each particular mill. The payback on both the soap separation and the via separations can be 3 months to 6 months or greater, depending upon the mill configuration. Now, these are the technologies that BDC believes are ready for deployment, that we personally have vetted, and there are a host of technologies that aren't on this slide. If you have one that you think ought to be on this slide that you want to bring to our attention, we'll be more than happy to look at it. There are a couple right now that we're looking at that could be candidates for this slide, but we haven't completed our due diligence. In some cases, due diligence is exceedingly hard when the technology provider declares everything confidential and won't discuss the details, so we can get to the fundamental theory and make the fundamental calculations. But we're happy to consider any recommendation that you may have. And if you have an interest in these technologies or any other technology, and you think your mill or your corporation wants to hear more, BDC is more than happy to create a webinar for your mill or your corporation and focus in on those technologies that are of most interest to you. And in that case, There are technologies that aren't on this and subsequent slides. We'll have to do our due diligence to put them there. Next slide, Harry. These are technologies where they're a little further to the left. And I'm not going to go through all of them because of some time constraints. But these have midterm impact. So I'll just cover the column that's far most to your right, starting at the top with Licella. That's hydrothermal liquefaction of wood. Because it's a water-based process, the water content of the incoming raw material is not of concern. That's a huge advantage. For example, in the next process down, Ensign, which is the pyrolysis of wood, you have to dry the wood to perhaps 10% moisture before you can pyrolyze it, or you get unwanted consequences. The Licella process is a 3-stage catalytic process. Wood is dissolved and converted ultimately into bio-oil. That bio-oil is very different than pyrolysis oil, as in that it has lower oxygen content. And that bio-oil has been looked at by several refineries, and that bio-oil can be sold to refineries, and they can, petrochemical refineries, they can put it in their process and use it as an additive to oil. And that process also happens to take wood, residuals, forest residuals, and even plastics. And so some of the mill waste streams can go into this process as feedstock. Ensign pyrolyzes wood. They have a demonstration process in Renfrew, Ontario, Canada, 100 miles west of Ontario. They take wood, dry it, and pyrolyze it, make pyrolysis oil, and have developed a very unique way to make heating oil out of the pyrolysis oil, and have contracts with a number of places to replace heating oil with wood-based pyrolysis oil. Fulcrum is in startup right now. That is a process where they start with the trucks that take municipal solid waste to a landfill. And rather than go into the landfill, these trucks will go to the Fulcrum plant that processes them. They can't go to the landfill because EPA doesn't give energy credits, tax credits for harvesting landfills. So they have to take the truck to the Fulcrum site, sort the glass and the metals and the heavies out, and essentially come up with an organic fraction. That organic fraction is fed to a TRI gasifier. It's a bed gasifier, and the bed is heated by pulse combustion because of the very high energy transfer in pulse combustion. So this thing doesn't burn like a boiler, it hums like a rocket. That creates syngas. There's no oxygen injected in this process. The syngas is essentially the main syngas is carbon monoxide, carbon dioxide, and hydrogen. So this facility actually makes hydrogen. You're hearing a lot about this these days. TRI has been making hydrogen for a couple of decades. The gas is cleaned because it has contaminants like sulfur, which are poisonous to the catalysts down to the part per billion range. TRI has developed some proprietary technology to remove these harmful trace elements. And the syngas goes to the cobalt catalyst in the Fischer-Tropsch reaction. The cobalt catalyst converts the gas to liquids, in this case, Fischer-Tropsch liquids, and the Fischer-Tropsch liquids will be further refined to produce sustainable aviation fuel. Now at the bottom, we have Andritz A recovery. And A recovery is a concept. If you are not familiar with that, I would urge you to visit the Andritz website to look at the total concepts for A recovery. We just did a webinar, the BDC did a webinar on that last week. But one element in the A recovery is the high energy efficient boiler. If you've not looked at a Herb or other vendors make these too, they call them different names, but if you haven't looked at any of these, we would urge you to do that, because essentially the boiler is being reconfigured to produce much higher pressure steam. That gives you higher thermal efficiency in the boiler, but more importantly, it gives you higher thermal efficiency in the steam turbines. Then these high energy efficiency boilers are being installed in new mills, and the new Suzano mill in Brazil will have one of these, and they will not only make all the steam and energy the pulp mill needs, but they export 80 megawatts of power for local use. And we talked earlier about the need to make more energy efficient mills. With the technologies we have on the table, if you could afford it, and you can't, but if you could afford it, there isn't a craft mill in the world that couldn't be made to be energy self-sufficient. In the interest of time, Harry, we'll go to the next slide and sort of wrap it up there. We've talked about these things, but you have to quantify them. And this is our table to quantify these technologies, if appropriate, in a single mill. The first column on the right describes the fundamental costs, and these costs were, well, the costs in the base case came from studies like the DOE bandwidth study that we talked about earlier, from other studies that have been made and published. And it looks like when we did this slide in 2020, and go down to the first subtotal, and the average cost of making pulp in the United States is $470 a short ton. There are two things below that we need. If we're going to look at costs, we have to figure out how to put in one simple table things that will add more value that are not cost related. And what we did is when there's a profit from, say, additional soap and tall oil, we converted the profit to a negative cost, so that when you get to the grand total taken as cost reduction, you can compare all these technologies. The first column is simple energy reduction. BDC's first webinar showed 3 energy experts and what they have typically done in mills, and we here just said we took the energy costs from base case of $70 a ton to $60 a ton. Those are energy reduction studies which have, if any capital is required, they have an extremely short payback, 3 months, 6 months, something like that. It's possible to go into a mill and have an immediate payback if you get the right energy team. There may be 2 or 3 such teams, so be careful who you pick to do these studies. We have recommendations on people that we have experience with. There are others, but be very careful when you pick that energy reduction team. Make sure you get expert results. The next column was for lignin removal. As you go down the costs and come to energy, you'll see that the lignin removal does consume energy, and that the energy costs there go up. And that energy cost is the steam replacement cost for the lignin that you took out. It requires some more labor because there's a separate facility to do that. So the subtotal in the lignin removal, it doesn't look very good. But when you go down to the profit per ton for new products and you're selling that lignin, and here we assumed what's turning out to be a reasonably low selling price, $600 a ton, you add back, you can take credit for that as a cost reduction. That's not a standard accounting way to do this, but the net effect of that brings the 470 number down to 435. Very attractive. The next column shows sludge to solid fuel. And by the way, after the base case, these are all BDC calculations. Full soap removal shows a slight increase because there's a slight increase in cost to take it out, but the profit per ton for added pulp production and the profit per ton for new products bring the grand total also to a very attractive number. Here we have not taken credit for the removal of any evaporator fouling, and we have not taken credit for increased burner efficiency in the recovery boiler. Those are mill specific, and when you're doing averages, it's hard to do things like that, but they may be applicable in your mill. And that brings the total cost of soap removal down to 460 versus 470, so you're a lot better off. Next column is for weak black liquor concentration, and then is the sum of all the opportunities. So if all these technologies happen to be applicable and happen to be affordable for your mill, then it's possible to bring a cost of 470 down to a cost of 403, or a savings of $67 a ton. That is huge. That is a huge impact. And once 2 or 3 mills do this, the rest of the industry has to follow to be cost competitive. So, and a lot of these things, the way I think about them is the same way I think about taking a cocktail olive out of an olive jar. The first olive is very hard to get out. It's messy, and the first olive can pop and go anywhere. But after you get the first one out, if you do it right, the rest of them float to the top. There are some landfill diversion opportunities which we're working on now. We want to talk about that for 1 minute. So go to the next slide, Harry. And what we're looking at here is to characterize the landfill contents, that what the mill takes to the landfill in solid form, usually containing about 40 to 60% water, and especially from the recycled mills, because that stream is a lot more pure than from a craft mill. We want to determine the volumes, the concentration, and a cost to deliver this to potential users. We've identified some potential users. Those potential users have expressed an interest. They want to learn more. They want to talk to mills, and we're facilitating that now. And the idea would be to convert this for a recycled mill, huge stream of waste material to a valuable product, one that benefits society. And in doing so, it will make this mill a lot more environmentally friendly and a lot more sustainable in the long run. And so we'll keep everyone posted as we make progress in this area. And I think we should go to questions now, Harry.
Okay, so we do have our first question in. Can you hear me?
I can hear you.
Perfect. We do have the first question in, and I had sent it to you in the chat. But the question is, how does the ligno-boost process precipitate the craft lignin?
What was that question again?
How does the ligno-boost process precipitate the craft lignin?
Okay. You take the black liquor at about 40% concentration. Let's make this case simple. You take it to a tank. It's got a pH of 11 or 12 or whatever the pH is. You drop that pH to something under 7, and the lignin precipitates out. The lignin is soluble in the craft black liquor because of the high pH. When you neutralize the pH, the lignin is no longer soluble, and so it must precipitate, and it simply drops to the bottom of the tank, and you take it out from the bottom of the tank.
Okay. I don't see another question coming through as of yet. I actually had written down, could you revisit the Shell Technologies screen? You had mentioned that the hydrothermal liquefaction of the bio-crude oil to fuels underwent a certain process. Can you tell us what that process was again? I didn't quite catch it.
Yes, the Lysella process starts by taking wood of any size that's pumpable. So the wood doesn't need to be chopped to chip size like you would do in a pulp mill, but any size that's pumpable. They pump the wood into vessel number 1 and cause that vessel to be under high temperature and high pressure, just below supercritical. They never quite get to supercritical conditions because supercritical conditions break certain carbon-carbon bonds, which they don't want to do. So it's just a few degrees south of supercritical. And there's a catalyst in stage number 1 that helps liquefy the wood. So it goes into this vessel in a continuous process. By the time it exits vessel number 1, the wood is liquefied. It goes on through 2 other stages. They maintain the pressure and pass that over 2 other catalysts. So they have 3 catalysts in total. These are relatively inexpensive and relatively long-lasting catalysts. The product comes out, and there are 3 things in the output of the product. There's bio oil, there's water, because you can actually make water in this process because the wood can have 35% water when it comes in, and the oil will have no water in the oil when the oil comes out. So if you were to pump what comes out into a tank, the non-soluble inorganic fraction, the dirt and the rocks, drop to the bottom of the tank. Then there's water in the middle of the tank, and the oil floats on the top of the tank. And there's a decanting mechanism to separate all 3, but the separation process is pretty easy. This bio oil has low oxygen content, 10-12%, versus pyrolysis oils, which typically can have 20-30%. and the oxygen content is a problem for the refineries. So the refineries would have a preference for this type of oil, bio oil versus other types of bio oil, and that bio oil can be shipped to a refinery. Now, there are certain EPA regulations that in the United States which will not allow renewable energy credits, or RINs, renewable energy identification numbers. You cannot apply to EPA and get permission to use the process if you ship your bio oil from plant A to refinery B and refine it there. You may do this, of course, and there's nothing preventing you from doing it, but you just won't get renewable identification numbers when you do it. There's a group working on legislation to change those EPA regulations, but right now you have them. The Shell technologies are technologies being developed to put facilities on site to convert the bio oil to a usable oil on site so that it can use these RIN credits as part of the economic justification.
Okay.
Ben, I'd like to add for the audience understanding is that the Lucilla process will also work in the same manner on plastic, any organic, in fact. And that is a process that is in consideration for this recycle waste that's going to landfill right now that you mentioned at the end of your presentation. It's plastic contaminated with fiber, and it's wet. It fits very well with the Lucilla process.
Yeah, and we should also mention that the first Lucilla process to start up will be on plastics. There's a plant being constructed in England right now, which will start up in 2022, where plastics are being converted to a bio oil, slightly different catalysts, slightly different bio oil, but same song, second verse.
Okay. So I have two more questions, and I want to make sure we're respectful of everyone's time, but this one was modified just slightly, but it reads, from all technology examples you mentioned, which would you consider, or which do you believe may be preferable for next generation paper mills like revolutionary technology?
Let me flip back to this slide. Harry, maybe you could do that with all the technologies on it.
This one or
Slide 15. We believe that all of these technologies are applicable. The ones on the far right, Lucilla, Ensign, Fulcrum, and Andritz are being built and used today. So you can buy them. They're commercially available. And it's just a question of, do you have the feedstock that be guaranteed for 20 years? And can the facility be profitable based on the economics of the location that you've selected? Via separations is one that we think once it's been demonstrated at commercial scale, and hopefully that'll be next year, it'll be applicable to all kraft mills and maybe things beyond that. NetGen, as soon as that, we didn't discuss that technology, but that's another way to take lignin out of black liquor through the use of enzymes. You simply bring the weak black liquor to to a new place in your facility, add enzymes to the weak black liquor. The enzymes reduce the molecular weight of the black liquor, and they reduce it to a number of different sizes. And hopefully in the end, you'll be able to sell all the sizes, but for the first plant, you pick out the particular molecular weight you're interested in, take it out by ultrafiltration, and you get a unique lignin. This is, you know, you can think of the lignin that comes out of a lignoboost process as crude lignin, because it's got all the molecular weights, just like crude oil has all the molecular weights of petrochemicals. This particular lignin fraction is a particular molecular weight. It may have a particular application, and you may choose to commercialize that first. The other black liquor, the ones you don't use, can go back to the weak black liquor tank and be reused in the normal craft process. So it's a very flexible process, has very potentially high impact. The first product that's being looked at is called methanogen shield. That is a certain molecular weight size lignin that, when taken to a linerboard machine and applied to the linerboard, you can be sprayed on in the Fourdrinier, or if the linerboard machine has a size press, it can be put on in the size press application. It increases the strength and increases the durability of the linerboard under high moisture use conditions. Linerboard is one of those products that gets shipped around a lot. It's exposed to a lot of different temperature and moisture conditions, and one of the important tests in linerboard is how do I maintain my strength properties during use, and particularly during use in high moisture conditions. This methanogen shield seems to improve the use by significant percent higher for recycled products than for virgin products, but improves the moisture durability, improves the strength, and looks at this stage very promising. But we have to go to a demonstration stage with this before we know.
I would add to that, Ben, that Lacilla has opportunities. You know, they're not going down this road at this point in time, but they have the opportunities to break down black liquor, and you know, could potentially take a stream off and reduce the amount of black liquor going to the recovery boiler, opening up capacity, or in some cases there's a potential to see it as a replacement for a recovery boiler in the long run. We're talking about a lot to be proven before it could do that.
Yeah, if there's one technology that I think has got a bright future in the pulp and paper industry, is hydrothermal liquefaction. Sea Green also uses that on particular sludges to convert the sludge right in the mill to energy briquettes, which can be burned in a mill solid fuel boiler. And that's a process of hydrothermal liquefaction.
Okay, perfect. Well, gentlemen, thank you so much for your presentation today. I know that there's certainly a tremendous amount of technology that's out there. So this is looks like it's just getting the tip of the iceberg as we get started down this road. I think that we've all heard everyone chasing the date for sustainability, and that date continues to get moved up. So this technology will be increasingly more useful and necessary as we move forward down that path. With that, I know that we're a little over our time today, so I'm going to finish everything up. And so I want to take the time to say thank you to all of our presenters who have taken the time out of their schedules to be part of our webinars. Again, all of these are on our website, and the BDC presentation today will be released as soon as we are finalized with the video. So be on the lookout for an email with that information. So with that, I want to say thank you to everyone. And I'd also like to say a big thank you to our office administrator, Wendy Kidd, who has been assisting getting everyone registered and making sure that we have all of the necessary information as we've been attending the webinars. So thank you all again, and we hope that you have a wonderful rest of your week. I will be sending out an email prior to Christmas. So if I don't see any of you all or talk with you before then, we hope that all of you have a lovely holiday with your family and your friends. So be safe. We're looking forward to 2022. Thanks, everyone.